So we just discussed adding, subtracting, multiplying, and dividing functions. Now we're going to talk about composing functions. Some notation you may not have seen before is this open circle. Kind of looks like a degree symbol, but when you read it with respect to functions, it's read as f composed of g. Okay, that is the composition symbol. So f composed of g, or what we really say is f of g of x, okay, or g composed of f reads g of f of x, okay. So two different notations that mean the same thing or that reference a composition of functions are these. You might see f with the composition symbol, then g, or vice versa, or just as a series of parentheses. And really, working with it using this notation is a little bit more intuitive in terms of, experience that we already have in terms of evaluating functions. So when we're looking at a composition, we're basically taking one function and substituting it into the other. We're composing one of the other, making one up of the other one. So if we ask you to find f of g of x, you will be substituting g into f. F composed of g means substitute g into f. G composed of f means substitute f into g. The biggest mistake I see people making is not differentiating between the composition symbol and the multiplication symbol. So if it's an open circle, it's composition. If it's just a dot, it's multiplication. So you have to make sure that you are, not confusing the two. They are different. So, first example, for f of x equals 2x minus 9 and g of x equals x squared minus 9x plus 18, we want to find g composed of f, or we want to find g of f of x. Okay, so g composed of f, this is find g of f of x. And so what we're doing is we're just going to take our f of x, right, and evaluate g for that function, for that expression. So we have g of 2x minus 9, which is, so substituting 2x minus 9 into my function g, I have 2x minus 9 quantity squared. So you guys should be familiar doing this. It's just a matter of working your way through the notation. Minus 9 times the quantity, 2x minus 9, plus 18. Now we're going to go ahead and simplify. So 2x minus 9 quantity squared. Remember, you can't just square each term. You actually have to write out the expanded form, and then we're going to FOIL those two binomials together. I'm going to keep working as I go down. Distributing my negative 9. I have minus 18x, negative 9 times negative 9, plus 81, plus 18. FOILing these, so first times first is 4x squared, outer times outer, minus 18x, inner times inner, minus 18x, and last times last is plus 81, and we have minus 18x. I'm just rewriting all the stuff at the end. Okay, and just like anything, you always want to combine your like terms. So we just have the 4x squared. When I combine all of my x terms, negative 18 minus 18 minus 18 gives us negative 54. So that's minus 54x, and then 81 plus 81 plus 18, that all adds to 180. So g of f of x is this, or we would say that that is our composite function. So again, when we were adding, subtracting, multiplying, and dividing, If there's just an x here, our interest is in finding the function, okay? If there's a number here, our interest is in evaluating. So finding the composite function, we should end up with a function at the end. Okay, we're not looking for some specific numeric value. Though it could be that the composite function is a constant function. I mean, it's not unheard of that you would just get a number, but that would only be if all of your like terms added to 0. All right. So, the same two functions. So yeah, same two functions. We want to find f of g of -2. So again, since we have this number here rather than the variable, this is asking us to evaluate the composite function. Okay? So just like before, we can evaluate option 2, and I don't like all this, I'm just going to knock all that out. We can evaluate without ever finding the composite function, but we can also find the composite function first and then do our evaluation. So looking at our first option, the first thing that we would want to do if we're going to use this option is find the composite function. So what we're going to do first is we're going to find f of g of x. So again, this notation, f of g, we are finding f composed of g of x, okay? Or f composed of g of x is x squared minus 9x plus 18. And so substituting this expression into our function f, we end up with, I'm going to have to write it down here, 2 times the quantity, right? I'm plugging this in for this x here. So we have 2 times the quantity, x squared, minus 9x plus 18, and then the minus 9 at the end of our function. Simplifying, so I'm going to distribute the 2. I've got 2x squared minus 18x plus 36 minus 9, and 36 minus 9, doing our simplification, we get 27. So that's 2x squared minus 18x plus 27. Okay, so this is the composite function. This is f composed of g. This says evaluate the composite function for an x value of -2. So now that we have this function, we can simply substitute -2. So f of g of -2 is going to be 2 times -2 squared minus 18 times -2 plus 27. Okay, just making sure you can see that. So I square my -2 first. So -2 times -2 is 4. Then I multiply by the 2. So that's 8. So we have 8 plus 36 plus 27. And that is 71. Okay? So I can evaluate by first finding the composite function and then substituting in, or option 2 is just evaluating without ever finding the composite function. So back to notation, f of g of -2 is the same thing as f of g of -2. And so if I want to evaluate without finding the composite function, what I need to find first is this g of -2. So to find g of -2, we're going to substitute -2 into g. So g of -2 we have negative 2 quantity squared minus 9 times negative 2 plus 18. So that's 4 plus 18 plus 18, which is 40. So g of negative 2 is 40, so I can rewrite this as f of 40. And now all we have to do is find f of 40, and to find f of 40 you should know that you're going to substitute 40 into f. So f of 40, we get 2 times 40 minus 9, and 2 times 40 minus 9, we have 80 minus 9, or 71. And so you see, regardless of the method, we do get that same value. Okay? For this function f of x equals 2x minus 9, we want to find f of 1. So I'm going to do that using the second option. Again, I find it easiest for me to rewrite this as f of 1. And I know that I need to simplify or find out what the value of this is first. Right? We want to find this first. So finding the value of f of 1, we have f of 1 is 2 times 1 minus 9, or negative 7. So, since f of 1 is negative 7, I'm just going to replace it. Okay, I just replaced f of 1 with negative 7, and now I need to find the value for f of negative 7. So f of negative 7 is 2 times negative 7 minus 9. So we've got negative 14 minus 9, which is negative 23. So f of negative 7 is negative 23. Or f of 1, I get negative 23. Okay? Domain. So find the composite function and state its domain. Let's find the function first, and then we're going to work on the domain part. Okay? So finding the composite function, here f of g of x, so we're finding what f composed of g is, or what f of x plus 8, we're finding that function. So we need to take our x plus 8, and we need to substitute it in for every x in f. So we have 2 times the quantity x plus 8 minus 3 over 3 times the quantity x plus 8 plus 5, or 2x plus 16 minus 3 over 3x plus 24 plus 5, which gives us 2x plus 13 over 3x plus 29. So f of g of x, that composite function, is 3x plus 13 over 3x plus 29. Okay? Then finding the domain, it's a little bit funky because you have a lot of things to consider when you're dealing with the domain of a composite function. Now, if you go back to, let's go back to this example here. You know, when we're evaluating a function for a specific value of x, we first take this number, this input, and we substitute it into g. So here we had g of negative 2 equals 40. Then we take that output, right? G of negative 2 equals 40. So which means if I input negative 2 into g, the corresponding output is 40. Then we take that output of g and we input it into F to find this output here. So, when we're looking at domain of composite functions, we have to ensure that anything that I put into G will give me an output that is okay to put into F. Okay? Remember, in terms of domain, we have to limit any inputs that give us output values that are not real numbers. So, coming back to this. So, it says here, and it goes along with what I was just saying, that the domain of a composite function, f of g of x, is the set of all input values of x in the domain of G, where g of x is in the domain of f. Okay, or all values x such that g of x can be substituted into f and the corresponding output would be a real number. So the two concerns that you're going to need to address when dealing with the domain of composite functions is, or domain of any function, if you have a number divided by 0, that is undefined, right? Or that is not a real number. Also, if you take the square root of a negative, that is a complex number, which is not real. Okay? We are dealing in the Cartesian plane, so we need to make sure we're only working with real numbers. So, as I go through, I'm going to up here, I'm going to write my composite function down, and then I'm going to erase all that work so I have room to write. Okay. Bear with me here. Okay, so when you're trying to find the domain of a composite function, you always have to consider the domain of your input function first. Okay, so first off, what is the domain of G? Okay, this is my function G. And in terms of domain, I look at it and I think, well, do I have any x's in the bottom? Do I ever have to worry about substituting a value in here and having a number divided by 0? And that answer is no, right? There are no, like in this case, we will, but here we don't have a denominator that includes our variable, so we never have to worry about division by 0. Also, there are no square roots in this function, so we don't need to worry about the square root of a negative. So the only concerns that we have would be if we have a situation where we could do division by 0 or the square root of a negative. And so therefore, this function, I can input any real number for x and get real numbers back for y. So the domain of G is every number is all real numbers. Okay? Also, if you want to think about it visually, g of x equals x plus 8, you guys need to be able to recognize that as a diagonal line. Okay? It hits the y-axis at 8 and it has a slope of 1. So, if we do our graph, we look at our graph, we can see that the domain is every number from negative infinity to positive infinity if we scan left to right. Okay, so the domain of G is this. So like we said, we have to think about, okay, the numbers that go into G, and then we also have to consider those outputs. So if I put any real number into G, what is the range of G? Right? What are my outputs? So you can see visually it ranges negative infinity to infinity, but you can also see, if you put any real number in, you're going to get any real number back out. So any number from negative infinity to infinity we have in the range of this function g. And so once you get to this question, then can any of these values, which are the values of g of x, or I'm sorry, let's say, can all of these values be input into f, or be put into f? Okay? Is there any concern about getting division by 0 or a negative number? And that answer is, yeah, there is concern, right? If you put, looking at the denominator here, this denominator cannot equal 0, right? Our 3x plus 5 cannot equal 0, because if it does, then we'll have a number divided by 0, which is undefined. And so because of that, 3x cannot be negative 5, or x cannot equal negative 5/3. Okay? Or it's not just negative x, in this case it is. But what this is telling me is that I have to make sure that I don't ever try to substitute negative 5/3 into this function f. And so therefore, g of x cannot be negative 5/3, right? Because I'm going to have my values of x that I substitute into g, and those values then I would substitute into f. So I have to make sure that my g of x is not equal to negative 5/3, so that I don't substitute any, so that I don't get 0 in the denominator. So for g of x to not equal 5/3, this is my g of x, then that means x plus 8 can't equal negative 5/3. Or x cannot equal, and then just get out your calculator, negative 5/3 minus 8, you should end up with negative 29/3. Okay? So, what is the domain of my composite function? My domain is all real numbers except negative 29/3. Okay, and if we want to write that using interval notation, that would be every number from negative infinity up to negative 29/3, and then any number not including from negative 29/3 to infinity, right? We've got parentheses on either side, so that's how we would use interval notation to just exclude that single number. It is true, if you look at the composite function that you end up with here, you do see that you can just look to see, in this case, this number does correspond to the value that would make this composite function equal to 0. In general, you cannot just find the composite function and then look at the domain by looking at the resulting composite function. Every function that you get in this class, you will be able to do that, but this really is the process that you need to go through when finding the domain of a composite function. It's a long process, and you have to really understand what's going on. Okay, let's look at another example. Find the composite function and state its domain. So the composite function, f of g, so we're doing f of 3x plus 14, so that is the square root, right? I'm going to take my g, and I'm going to plug it in here for that x, so that's the square root of 3x plus 14 minus 2, or the square root of 3x plus 12. Okay, so my composite function f of g is the square root of 3x plus 12. So domain, first thing, we need to look at the domain of our input function. And domain of g, again, this is just a diagonal line. I can input any real number and the output will be real. So my domain is any number from negative infinity to positive infinity. The range of g, which is our g of x, is also any number from negative infinity to infinity. And so the question is, can I allow g of x to equal any of these numbers? Is it okay to put all of these numbers into my function f? Okay, remember when we're talking about the domain of any function, our two concerns, our one concern is division by 0, right, because division by 0 is undefined. And our second concern is taking the square root of a negative number, because the square root of a negative is a non-real complex number. So, looking at this, I know, well, x minus 2 has to be greater than or equal to 0, right? It has to be equal to 0 or a positive number, because if it's negative, then the output will be complex. So that means that my inputs, anything I put into f, has to be a number greater than or equal to 2. Okay? So in terms of this, that means that g of x has to be greater than or equal to 2. Because that's what I'm going to be. I'm going to be putting x into g, and then I'm taking g of x into f. So the stuff that I put into f, my g of x, has to be numbers that are greater than or equal to 2. So my g of x, my 3x plus 14, has to be greater than or equal to 2. Okay? So 3x has to be greater than or equal to negative 12. And if I divide both sides by 3, I get that x has to be greater than or equal to negative 4. Okay? So the domain of my composite function, so again, this was my composite function here, f of x equals the square root of 3x plus 12. And the domain is all values of x that are greater than or equal to negative 4, or every real number from negative 4 to positive infinity. And like I was saying before, in this case, if you notice that if you put numbers from negative 4 to infinity into this composite function, you will get positive values. But again, in general, it is not okay to find the composite function and then look at the domain from there. Okay, what have we got? One more. So for f of x equals x squared plus 6x minus 9 and g of x equals x minus 3, we want to find a value for x for which f of g of x is equal to g of f of x. Okay, so I'm just going to work my way through this equation that I have. f of g of x, we have to find f of x minus 3. For g of f of x, we have to find g of x squared plus 6x minus 9. Right? And we're wanting to find a value of x for which these two values, or these two, are equal, these two functions. So f of x minus 3, I'm going to substitute x minus 3 into my function f. So I'll have x minus 3, quantity squared, plus 6 times x minus 3, minus 9. I was going to write plus, let me erase that. Minus 9 equals g of x squared plus 6x minus 9. I'm going to take my x squared plus 6x minus 9 and substitute that into my function g. So we have x squared plus 6x minus 9 minus 3. Going through and simplifying all of this, we need to FOIL the x minus 3. I'm just going to write this separately here. So x minus 3 times x minus 3. If we FOIL, we have x times x, which is x squared, x times negative 3 minus 3x, negative 3 times x is minus 3x, and negative 3 times negative 3 is plus 9. Distributing the 6 gives us plus 6x minus 18, and then bringing down our minus 9. On the right hand side, I can see that negative 9 and negative 3 are like terms, so I'm just going to go ahead and simplify that now. And working on the left hand side, negative 3 minus 3 plus 6, we just have our x, bring down my x squared, sorry. Then negative 3 minus 3 plus 6, that is 0. And 9 minus 18 minus 9 is negative 18. So we have x squared minus 18 equals x squared plus 6x minus 12. I'm going to go ahead and